Welcome to E. Padasala lecture series in computer science. In this particular module, we are going to discuss about dynamic programming approach. Recollect for the past two modules we were talking about dynamic programming approach. In this module, we are going to review that and then we are going to discuss two important problems as part of that. The learning objectives of this particular module is to explain the dynamic programming, where we are going to review that. Then we are going to discuss an interesting problem called multistage graph problem. This is also very popularly known as stagecoach problem, where we have to find the shortest path between the source and destination. Then we are going to discuss about the traveling salesperson problem, which is a very popular problem in computer science domain. So, we will discuss traveling salesperson problem first, then we will discuss about multistage, then we will see how multistage problem can be modeled to solve the traveling salesperson problem also. Fine. Dynamic programming approach, which we have been discussed for the past two modules, are the design technique that is used to solve problems where sequential decision problem, where sequential decisions are to be made. So, recollect that I was telling you that dynamic programming is useful for solving optimization problems. So, we have a huge number of optimization problems in computer science domain. So, naturally the dynamic programming is an obvious candidate for solving those optimization problems. So, remember what we were talking in the last module. The important thing is we have to establish the recursive property that gives the solution of the instance of the given problem. So, this combines the problem and its subproblems. Then once a recursive formula is given, then we will solve the smallest problem first, then we will try to use those results to solve much more larger problems. So, the entire approach is called the bottom up procedure. So, the rules we have seen, each substructure is optimal. Principle of optimality, we stress that any solution to the given problem contains a solution for problems that are contained in that. Then all the problems that are involved are all overlapping problems. These are not independent as in divide and conquer strategy. Then we have seen that the popular methodology is the computation in bottom up fashion. So, that means we are going to solve the smaller instance first, then we will gradually go for much larger instances. So, the idea is not to recompute, but rather to reuse the solutions. So, we create a table as part of the problem solving, then we will reuse the entries of the table for computing the subsequent values. So, this is going to be the salient feature of dynamic programming. Fine. We will talk about one interesting problem called the traveling salesperson problem. Remember, in the very first module the complexity of this problem was indicated as a motivation for studying the algorithms. So, this problem is known under various heading like traveling salesman, traveling salesperson, etc. We will call this as simply TSP. So, in TSP the problem is you have a salesman, you are given n cities and you are given the distances between the various cities. So, you can imagine something like a map is given where you have n cities and the distance between the various cities are given. So, you can model this as a sort of directed graph. So, you have edge weight that represents the various distances between the cities. You have to start from a place. The salesperson is supposed to start from his town, hometown maybe. Then he has to visit all other cities only once, exactly once, and he has to come back to the original city. So, this is called a tour. So, a tour starts from a city, visit all other cities, and then you are trying to get back to the original city. So, this finds the shortest path between various tour possibilities. In other words, we have to find the minimum cost tour as part of TSP. So, there are various ways in which we can solve this problem. The brutal way of solving this problem was discussed as part of brute force technique. Probably you can recollect we were applying that methodology in a brute force manner. So, you just enumerate all the path, then you find out the shortest path and that gives the solution. But unfortunately, as I said earlier, the enumeration will not work because for every rise in the number of cities, you have more number of paths to contend with. Therefore, the problem becomes an exponential problem and it is very difficult to give a solution for traveling salesperson using the brute force method. So, we go for a dynamic programming approach for solving this. So, dynamic programming gives a slightly better solution compared to the brute force method. So, here we are going to compute the function g of I comma s. It is the shortest subtour given that we are in city I and we have to visit all the cities in S, then we have to come back. In other words, the whole approach of this problem is to compute this g of I comma s. This is illustrated in this particular diagram. Say for example, now I am currently in city I, then I am travel to city J, means the jth city is visited. So, that means I should not visit J again. So, that means I will explore all the possibilities from J, city J, and still we have to visit all the cities of the set S minus J, and we have to get back to the home city. this is what you say needed for finding the solution of the traveling salesperson problem. So, the core idea is going to be like this. I am going to find a g of I comma s. This is going to be the length of the shortest path starting from the vertex I, going through all the vertices in S and terminate at vertex 1, which is considered to be the source or the home city of the salesperson. So, the length of the optimal tour is going to be the minimum. I am assuming that I am starting from vertex 1. So, that means I have to I should not visit 1 again, therefore, it is v minus 1. It is going to be the minimum for k. K is going to be our intermediate city, and it is the distance between 1 to k and the function from k to I have visited already 1 and k I have visited now. Therefore, I can go to my home via any node except 1 and k. So, the minimum distance is what going to be the length of the optimal tour. So, what is the general form? The general form is going to be g of I comma s, which is going to be minimum of c of I comma j, which is going to be the weight, plus g of j comma s minus j. This is what the general form of this particular algorithm is all about. So, you can see exactly what is happening now. We have to find from the source vertex all the path, then we are going to store that into the table, then we are going to increase the set and we are going to recompute the length of the optimal tour involving the length that already we have obtained. So, before going for the formal algorithm, let us have the illustration. Let us assume that this is the graph that is given. This is TSP. So, I have to start from city 1, then I have to visit all other cities, then I have to come back to the home city. So, I have to find the shortest path of the optimal tour. Now, I will start with S. Remember, I was telling you that S is nothing but the set of cities. So, initially it is going to be null. So, my function g of 2 comma 5, that means the cost of reaching the home city 1 from 2 reduces to c to 1. So, it is going to be 2. So, in the graph I have not given the cost. So, you can observe and note that c to 1 is going to be 2. Similarly, I can find 3 comma 5, it is going to be c 3 1, it is going to be 4, and 4 comma 5 is going to be 6. So, this is our first level. So, now what is the next step? The next step is we have to increase the size of S. So, if we increment the size of S by 1, then the possibilities becomes more. Suppose if size is increased, then the possible values are 1 to 3. Therefore, if S is going to be 1, then we have to find g of 2 comma 1, then g of 3 comma 1, then if s is going to be 2, we have to find g of 1 comma 2, like that. So, in other words, it becomes like this. What is the cost of starting from 2 and going via the vertex 3? So, the answer is it is the cost of moving from 2 to 3 and the cost of moving back to hometown from the vertex 3. Recollect the beauty of dynamic programming. G 3 comma 5 already we have computed. So, all we have to do is we have to plug this value here. So, cost of 2 3 is going to be 5, then 3 comma 5 is 4, therefore, it is going to be 9. So, keeping this template, we can keep on computing g of 2 comma 4, which is going to be c of 2 4 plus g of 4 comma 5, and g of 3 comma 2 is nothing but c 3 2 plus g 2 comma 5, and I can find all possibilities like starting from 3 going via 4, and similarly starting from 2 4 going via 2 as well as 3. So, in other words, these are some of the possible computations when s is going to be 1. Now, we have to increment s. So, that means now we have to increase the size of 2. So, that means now I consider the possibility of starting from 2 and going via 3 comma 4. So, just to see carefully what is happening. So, g of 2 comma 3 comma 4 is nothing but cost of going from 2 to 3 and the cost of starting from 3 and going via 4. So, that means now you can see very well c to 3 is going to be 5, and this already we have computed in the earlier iteration. Now, simply plug. So, the minimum is going to be 19. So, using this particular logic, I can find the g of 3 comma 2 comma 4 as well as 4 comma 2 comma 3. So, I can compute all these things with s equal to 2. Again I have to increment s. So, now s becomes 3 now. So, that means the intermediate node is going to be 3. So, that means you can see very well now I have to find the shortest path 1 comma 2 3 4. So, that means it is going to be the minimum of c of 1 2 plus g of starting from 2 to 3 4, like that I can write. So, when we plug the values of the previous iteration, you can see that the minimum cost is going to be 18. In other words, the shortest path from the source to destination is going to be 18. Fine, one side of the problem is solved. The next question is find what are the path through which we have to traverse to get a cost of 18. To get an answer for this, all we have to do is we have to record k which gives the minimum at every stage. So, that means now you can see very well the minimum is obtained from traveling from C 1 3 and then G 3 comma 2 comma 4. So, that means if we keep on tracking that, you can see that the path is recovered. So, now the path goes from 1 to 3. Now, we have to see from 3 which path gave the minimum, which was P of 3 comma 2 comma 4. So, therefore, now you have come to a conclusion that from city 3 we have to visit 2. So, that means there are only 4 vertices. So, 1 3 2 is visited, therefore, I can go back to the city 1. So, in other words, I will visit 1 3 2 4 and then I will go to 1 again. So, this is going to be the path recovery of this particular problem. What is the complexity of this algorithm? The complexity of this algorithm is from every city we have to visit every other city. So, that means you can see that the complexity of this turns out to be something like order of n square to power n. So, that means still it is an exponential algorithm only, but if n is very less, then obviously this algorithm is feasible. But if n becomes very large, then it is becoming very difficult. The related problem is called the multi-stage problem. This is also called as the stagecoach problem. This is a very popular problem in computer science. The idea of the stagecoach problem is that the salesman is traveling from one town to another town using a stagecoach. He has to reach the destination. So, the aim is you have to find the shortest path from source to destination using all the intermediate cities. So, that means the logic is we have to take multiple decisions at various stages, and ultimately we want to find the minimum cost of the trip, especially in the case of multiple path. First, we will discuss a problem. From that we can come to a conclusion how it really works. First, we will try to define a multi-stage graph. Multi-stage graph means the graph is arranged in such a manner that you have lots of stages. So, consider this scenario where you have from 1 you have edge to vertex 2, 3, 4 and 5 with this particular edge cast. So, similarly, this is your stage 2 to 3 with this cast, and this is stage 3 to 4 with this particular cast, and from stage 4 to 5 with this particular cast. So, the problem is very simple. You have to start from vertex 1, then you have to end in vertex 12, which is going to be your destination. You have to find the shortest path. So, you are going through various vertices involving stages. Okay. So, the logic is how to solve these sort of problems using the dynamic programming approach. Fine, we can solve this problem like this. Dynamic programming, as you can recollect, involves in dividing problems into sub problems. So, we can also divide this problem into sub problems using the concept of stages. So, we can take one stage at a time and we can solve that particular problem, then we can find what is the optimal, and using that we can backtrack and we can solve the next stage, and stage wise we can solve. This is called the reasoning. So, we have two types of reasoning. One is forward reasoning and another is backward reasoning. In forward reasoning, we start from your destination. First you try to solve the problems that leads to your destination, then from right to left you are coming towards your source. So, given this particular scenario, now we will take the last stage and then we will try to solve. So, from the last stage means stage 4 to 5. So, your cost is given in the previous table. So, stage 4, the cost between 9 and 12 is 3, and stage what you say 4 comma 10 is going to be 1, and 4 comma 11 is 4. So, this is what your scenario is all about. So, you can see backward reasoning means you are coming from your destination. So, you have to find what is the minimum. So, minimum is 4 comma 10 is going to be the minimum. Okay. So, now we proceed to the next immediate stage, that is going to be stage 3 to 4. So, in 3 to 4 you can see very well this is stage 3. So, we have to compute the cost of 3 comma 6, 3 comma 7 and 3 comma 8. So, cost of 3 comma 6 is nothing but the minimum of what you say cost 3, and from we have to see from stage 4 to 9. So, that means I have to use this particular table effectively. So, that means it is going to be 3, then I have to find the cost of reaching your destination from the node 9. Similarly, I can find via node 7 and node 8. So, now I can compute all the things. Now, you can see very well you have the minimums of everything. So, next I will go to stage 2. So, that means I have to find the optimal choices at stages 2. So, you can see the computations, then finally I will come to stage 2. So, now you can see very well it is going to be 3 plus cost of 2 comma 2. So, your source is going to be in stage 1. So, it is going to be you can see from this particular table that 1 to 2 is going to be 3. Therefore, it becomes something like 3 plus cost of 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, which you find in the previous iteration. Substitute everything and find the minimum, that is going to be 12. So, this is going to be the shortest path from source to destinations. So, this is the formal algorithm. You can see that the key point is you have to choose vertex x such that C of j comma k plus cost of k is going to be the minimum. So, you can keep on adding that as a set of decisions. So, this is the formal algorithm, and this is going to be the path recovery. Path recovery is very simple. We have to record the k which gave the minimum. So, by keeping track of k, we can find the shortest path from your source to destinations. What is the time complexity? Time complexity is going to be theta of n cube. Then space efficiency is going to be theta of n square. The same thing can be done in backward reasoning also. In backward reasoning, you will start from source. So, you can see that the same logic, but we will come from your source side. So, you can use this problem to solve the other optimal resource allocation, TSP, etc. So, in summary, we can say that TSP problem can be solved to some extent by dynamic programming. Multi-stage problem is very important. It can be solved using DP approach. Thank you very much. Next module we will come up with a new set of problem to illustrate dynamic programming approach. Thank you.